This lesson is on the curl of a vector field. So we're starting with this vector field f of x, y, z equals negative y, x, z. And quickly, let's remind ourselves of what the divergence was. And the best way to remember that is the del operator dotted with the vector field. So we get the partial of x, comma partial of y, comma partial of z, dotted with negative y, x, z. So the divergence of f becomes the partial with respect to x of negative y plus the partial with respect to y of x plus the partial with respect to z of z. So the divergence of f is this scalar 0 plus 0 plus 1. So the divergence of f is 1. Let's take a quick look at the graph to see if we can make sense of that. So looking at these points up here, if you pick a point, you can see that it's flowing out from that point. It's not flowing into that point. Same thing on the bottom of the graph. If you pick a point, things are flowing out from that for the most part, which reinforces our idea that the divergence is a positive number. But we want to go beyond divergence and talk about something called the curl. So what exactly is the curl? So let's talk about that. Now again, divergence was the dot product of that del operator with the vector field f. The curl of f, easiest way to remember, it's the cross product of the del operator with f. So let's go ahead and compute that for this problem. Writing it this way, we will then build our matrix. And this is what we have. So let's go ahead and do our evaluation. And we see in the I direction, we get partial of y, partial of z, x, z. In that j direction, partial of x, partial of z, minus yz. And in that k direction, partial of x, partial of y, minus yx. So doing our computation, we get curl of f equals, in the I direction, partial of z, partial of y of z, which is 0, minus partial of z of x, which is 0, minus j times partial of x of z, which is 0, minus partial of z of negative y, which is 0, plus k times partial of x, which is 1, minus partial of y of negative y, which is negative 1. So that the curl of that vector field will become 0, 0, 2. So what exactly does that mean? So this is the basic idea of curl. If you take a very, very small sphere and place it in a vector field, how will that sphere spin? Now you'll notice this vector on the top of that ball, that's the axis of rotation. That's the direction of the curl vector, and how fast it's spinning gives us an idea of its magnitude. So in our case here, we expect that the curl vector will be 0, 0, 2, that it will always have an axis of rotation parallel to the z-axis. So if we look at our vector field, you might be able to convince yourself of that. Here is the x, y, z equals 0 version of this. You can see the way it's spinning, and of course, that little sphere's axis of rotation would be pointing up. If you look at the 3D representation, a little harder to convince ourselves of that, but you might be able to, that indeed that's the way it's going to spin. But that's what that represents. Curl talks about how it's spinning in terms of its axis of rotation and the speed with which it is spinning. So let's take a look at another example. So we're given this vector field. Let's quickly find the divergence of f first. Recall the divergence is del dot f, del being partial with respect to x, partial with respect to y, partial with respect to z. So partial with respect to x of the first piece plus partial with respect to y of the second piece plus partial with respect to z of the third piece. And what does that give me for div f? And we get div f equals 4y, a scalar, not a vector. Now, how does the curl differ from div f? Div f is del dot f, curl f is del cross f. So let's build that matrix. Remember, it goes plus minus plus across the top. So plus I times his minor minus j times his minor plus k times his minor. In the I direction, We have partial with respect to y, partial with respect to z of x squared plus z squared 2yz. In the j direction, what do we have? Partial x, partial z. Two xy, 2yz. And then in the k direction, what do we have? Partial x, partial y of 2xy, x squared plus z squared. So let's do our computation. In the I direction, partial of y, 2yz, minus partial of z, x squared plus z squared, minus j in that direction, partial of x of 2yz, minus partial of z of 2xy, plus in the k direction, partial of x squared plus z squared, minus partial of y of 2xy, which gives me, in the I direction, 2z minus 2z. In the j direction, partial with respect to x of 2yz is 0, minus partial with respect to z of 2xy is also 0. So we're 0 in the j direction. Plus now in the k direction, what do we have? Partial with respect to x of x squared plus z squared is 2x, minus partial with respect to y of 2xy is 2x. Also 0. So when all is said and done, it looks like curl of f is the 0 vector, 0, 0, 0. So what does that mean? If curl of f is the 0 vector, i.e. 0, 0, 0, we say the vector field is irrotational. So in our case, we have an irrotational field. So here is our 2D version of this, looking at it on top. And here's a 3D version. So irrotational, that is going to mean something to us. We're not necessarily seeing it here. But if a vector field is irrotational, it is a conservative vector field. That will have important meanings in physics and engineering, but for us in mathematics, that means we can find a potential function f such that the gradient of little f will equal big F. So there's many equivalent things we can say here. Big F is an irrotational field. Big F is a conservative vector field. Big F is a gradient field. Now our goal is to find the potential function little f. So how do we do that? We know it has to exist because it's irrotational. Find the potential function little f of x, y, z. So we want little f to be a potential function for big F. If it is a potential function for big F, then the gradient of little f has to equal big F. What is the gradient of little f? That's f sub x, comma f sub y, comma f sub z would have to equal big F, 2xy, x squared plus z squared, 2yz. Now we have to reverse these partial derivatives. That gets a little tricky, but this is what we're aiming for, and our goal is to find f of x, y, z. Keep that in mind. Our goal is to find f of x, y, z. So let's start with the fact that f sub x is 2xy. So if that's the case, what could f of x, y, z be? Well, it perceives y as a constant, or even 2y as a constant. The integral of that would be x squared y. But not just that. This is a function of x, y, and z. So as far as x is concerned, y behaves like a constant, and so does z. So this would be plus any function g of y comma z. So we get that is our current version for f of x, y, z. Now, what can we say next? We can say that f sub y has to equal x squared plus z squared. That's helpful. But what else is f sub y? F sub y is the derivative, partial derivative with respect to y of this. So let's consider that. F sub y is the partial derivative with respect to y of x squared y plus g of yz, which would be partial derivative with respect to yx squared plus g sub y of y comma z is my f sub y. But again, f sub y equals x squared plus z squared. So if that's the case, what is that telling me then? G sub y of yz has to match z squared. So let's say that. So G sub y of yz has to match z squared. Well, if that's the case, then what is g of yz? Integrating that with respect to y, that would, of course, be yz squared plus some function of z and z alone, because that's what's going to behave like a constant here. So what that does for me is that tells me what g of yz is. I can move that up here to say what f of xyz is. Now that is x squared y plus, we just said g of yz was yz squared plus h of z. And that brings us to our third piece here. So our third piece being f sub z equals 2yz. But keep in mind where we at currently. F of xyz is x squared y plus yz squared plus h of z. If that's the case, then what is f sub z? The partial with respect to z of x squared y is 0, plus the partial with respect to z of yz squared would be 2yz, plus the partial with respect to z of h of z would just be h prime of z. But what do we know? What is f sub z? Looking at the top of our page here, f sub z was 2yz. So if f sub z equals 2yz, that would mean that h prime of z is 0. So h of z could be any constant. We're just looking for a potential function, so I'm going to let h of z equal 0. And now that enables me to go ahead and finish up my version of f of x, y, z, my potential function. So what do we have? We have potential function f of x, y, z equals x squared y plus yz squared plus 0. Just for kicks, let's go ahead and do a quick check. What is the gradient of little f with respect to x? 2xy. With respect to y, x squared plus z squared. With respect to z, 0 plus 2yz. And that is the same as big F. And we knew that we were going to have a potential function because the curl was 0, which meant that the vector field was irrotational, which meant that it was conservative. Therefore, we have a potential function.